So, hello everyone. Welcome back to ML Observability area. My name is Nadia, and I'm a senior machine learning engineer at NILAS. Today, I'm really excited to be here to have the opportunity to introduce one of our amazing speakers. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speaker after the presentation. So let's start. Our speaker is Reah Miyara. Reah is head of product at Arize AI, a startup focused on ML observability. He joins Arize from Google AI, where he led product development for research tools and infrastructure related to graph-based machine learning, data-driven large-scale optimization, and market economics. Reah's experience as a team and product leader is extensive, building and growing product across a broad cross-section of the AI landscape. He has played a pivotal role in ML and AI initiatives at IBM Watson, Intuit, and NASA Jet Propulsion Laboratory. Reah also co-led Google Research Responsible AI initiative, confronting the risk of AI being misused and taking steps to minimize AI's negative influence on the world. He has a bachelor from US Berkeley electrical engineer and computer science program and was the founder and president of the CAL UAV team in 2014. Please join me in welcoming Reah Miyara.
Thank you so much, Nadia, for the introduction. Hi, everyone. As you just heard, my name is Reah. I'm head of product at Arize AI, a leading ML observability platform. And in today's presentation, I'll be covering what ML observability is and why it's a critical piece in the ML stack. Jumping into the agenda, we're going to talk about some of the challenges you see in productionalizing machine learning, and specifically what it means to take a model from a research environment to production to the real world. We'll define what ML observability, this hot topic that you've been hearing about, is, and discuss why it's important. And then I'll jump into and kind of gloss over some key characteristics of your ML observability, of what a good ML observability practice might look like, and what you should expect of a solid ML observability platform. Taking a model from research to production is hard. Generally, the starting point for building any ML model starts in some sort of controlled research environment. Maybe it's your Jupyter notebook. But the journey from taking this model and pushing it out into the real world could be really difficult. Oftentimes, you may need to rewrite the model in a totally different language. You'll need to figure out how to handle various feature transformations in an online environment. And then there's always this question of whether the model is even worthy of production in the first place. Like, is it ready to be deployed? I mean, this model is making business decisions that are critical to your user's experience, your business's revenue, so on and so forth. And the truth is, after spending years at IBM Watson and Google AI, I've noticed the mantra is the same. When working at these top ML groups and these decacorns, the sad truth is most companies don't have the adequate tools or infrastructure to really understand how their model is performing in this new chaotic real world environment, and especially not kind of when something goes wrong, figuring out what went wrong and why. And I think, COVID is a real great example of this, because you had all these models that people spent, countless of hours training and that were working well in this controlled environment. And then in a post-pandemic world, they were not performing as expected anymore, right? So again, real world means uncontrollable variables, changes from world climates to human behaviors, and even things like malicious adversaries. And so, realizing that from a business standpoint, machine learning is expensive. Machine learning is, your models are tied to high value use cases and oftentimes fail silently. You have to understand that one-off scripts, graphs, they're not scalable long-term strategies for making sure your model is working as intended. And especially not for kind of troubleshooting and really reconciling the performance issues, the data quality issues that you might see, and reducing the time to value that it takes to kind of retrain, improve, and then redeploy that model. A quick overview of the ML infra stack. So there are tools like GitHub for version control, Datadog for infrastructure observability, and the ML stack kind of has its own buckets of tools and tool sets and platforms to help facilitate taking that model through the model development lifecycle. So you have your feature store, which handles online and offline feature transformations, your model store, or a central repository or registry for tracking experiments across models and model versions. And then we've introduced something called an evaluation store, which, like a model store, it keeps track of your model and your model versions. And this is kind of the core component that takes in all the different inferences that your model is outputting, as well as the ground truth from your users, if you're able to capture that, and maps it back to those model versions, model environments, to really give you a deep understanding of how your model is performing, as well as some of the other key characteristics, which I'll get to in just a few slides. So first off, defining ML observability. Oftentimes we get questions, is ML observability ML monitoring? And the truth is, monitoring is just one aspect of ML observability. ML observability, in addition to kind of claiming you're an ML observability platform, it's really a practice of gaining a deep understanding of your model's health and performance across the entirety of the model development lifecycle. So built on an evaluation store. And again, the evaluation store kind of has access to your data across model versions, model types, as well as your actual ground truth from, let's say it's taking in production data, validation data, and training data. And a good ML observability toolset relies heavily on this evaluation store, which is intended to scalably and intelligently index all this data to empower data checks, performance analysis, and monitoring and explainability. And so, data quality checks includes things like preventing or detecting anomalous inputs or type mismatches. Performance analysis means not just a kind of a single statistical number of your model's accuracy, but actually the performance across different cohorts, slices, and segments of your data. Monitoring and explainability. So monitoring is more of the proactive detection, right? Because as I mentioned just a couple slides ago, even these big companies, most of them are realizing that something went wrong only when a core business metric is down, or only when it's too late and there's already been a PR disaster, right? So taking a proactive stance, and explainability is being able to kind of link it back to, why did this happen at a global level? Why did this happen at a feature level? Why did this happen at the cohort level? Being able to really back up your decisions or your model's decisions. So this is just kind of one more explicit call out that monitoring is not enough. This is, again, kind of one of the most common questions we get. Do indicators that something went wrong, will that suffice? Or do I really need true ML observability? And the truth is, a deep understanding of your model means across the entire stack, not just a red or green light that's saying something went wrong, but it's helping facilitate troubleshooting and that root cause analysis so that you can quickly improve that model, retrain it, and then redeploy it into the real world. So jumping into the kind of 4 pillars or key characteristics of a good ML observability practice and platform. First one is drift. And I'll kind of dive into what each one of these is in a few later slides. Second one is performance analysis. Again, more than just a single number. Data quality, perhaps one of the most common issues that we're seeing across our key customers and across industries as a whole. And explainability, especially important for things, for heavily regulated industries with strict compliance laws, as well as preventing fairness or empowering fairness and preventing bias from your models. So first off, drift. What is drift and why is it important? Drift is change in your distribution over time. And drift is measured not just by your model's outputs, what your model is predicting, but also your model's inputs and the actual ground truth that you're able to collect from your users. So drift can occur when your model has gone stale, or if there's bad data flowing into your model, or even because of adversarial inputs when someone is trying to take advantage of your ML model or AI system. And there are several ways to kind of really quantify the distance between these distributions. And I'll actually get into that in the next slide, but drift is calculated as kind of change in a distribution over time, meaning generally what you do is you select or you define what's called a baseline, or what we at Arize call a baseline. It's a reference distribution where essentially you are saying maybe a training set, for example, is a good indicator of how my model is expected to perform in the real world. And this is what we see kind of happening over time. You're satisfied with your model's performance in training and validation. You deploy it into the real world, and then gradually over time, something ends up decaying. And so models are not static, and they're really good at data that they've seen before, but it's important to identify when data is starting to shift, whether, again, that's feature input values or the model's prediction themselves, or the actual values that you're collecting from your users, because models are not so good at things they haven't seen, right? And so being able to detect that drift over time is crucial to ensuring your model's performance in the long term. And so I alluded to this in the previous slide. Oftentimes, we get this question of, well, drift is super important. We want to make sure we capture it, but what should my baseline or what should my reference distribution actually be? And it really depends on your use case. And a good ML observability platform or toolset will give you the versatility, flexibility, and perhaps even the insights or recommendations as to what to select. So in many cases, people kind of oftentimes will select their training data and say, hey, my model performed super well in training. Let's compare how it's doing in production to what I saw when I was iterating on it and training it. And there are some issues with that. I mean, a common one is perhaps you are dealing with fraud, credit card transactions, perhaps. In the real world, fraud is kind of generally a highly imbalanced data set. So you may see less than 1% of fraud in production, but your training set was trained on 50% fraud and 50% not fraud, right? So you can see that there would be a kind of gradual shift in what you're seeing in production to how you expected or how you trained your model in the first place. In that case, we may recommend that an initial model launch period would be a better reference or baseline distribution. In many cases, it's common for you to have a seasonal or highly fluctuating use case where your model comparison may be more adequate or maybe better suited to compare across rolling production windows. And so that's, again, something that a solid ML observability platform should support. Being able to say, hey, I want my production data to be compared to last month's production data, and have that continuously roll and kind of reset to make sure that drift is being compared as seasons are changing or as demand is fluctuating. And of course, there's also this kind of live A/B case scenario where you're running longer term experiments to see how two different versions of models may compare across kind of a long-term experiment. And drift is great for noticing what we call kind of slow bleed failures, kind of this longer term decay. It's great for identifying trends, and in this case, one of our partners, this is actually a real use case where one of our partners was monitoring their marketing channels and saw that there was a drift in places they wanted to advertise. In this case, they were highly reliant on Facebook and Instagram. And over the course of time, as TikTok kind of ramped up with their target audience, they saw this new marketing channel kind of unseen value come into production. What it's not good for is kind of individual prediction level analysis or outlier detection, because kind of drift is, it doesn't solve everything, and it's not great at, it's really powerful in comparing kind of data sets or environments as a whole. But when you're trying to get that kind of more granular level prediction analysis, you may want to use some of the other tools that come with ML Observability platform. And it's important to note that it's not always the case that when a feature drifts, does it impact performance in a negative way. And again, kind of these, what I'll be walking through are key characteristics that are incredibly powerful when combined and are able to surface correlations across your model's performance and overall health. And so a good ML observability practice or tool should empower kind of this general flow where maybe there's some kind of proactive monitoring to detect drift between your baseline or reference distribution and what you're seeing in production. Send an alert through your incident management platform, and then be able to really kind of drill down into where the drift is happening across your predictions. Be able to tie that back to individual features or combinations of features to see is it input drift that's causing the model's predictions to drift. And at that point, you can start resolving the issue, perhaps through targeted upsampling to improve the model performance, or maybe some other method based on the insights you're able to capture. So jumping into the performance of a model, models generally fall into kind of two categories. Fast actuals, so these are models where ground truth or real kind of labels from your users can be linked back to the predictions in a relatively short period of time. One example of this can be seen in ride sharing. Perhaps you call an Uber and your estimated wait time is 10 minutes. In reality, you end up waiting somewhere closer to 15 minutes, right? So the prediction, there was a model that predicted you would wait about 10 minutes, and the actual that you saw was 15. So that's a relatively fast actual there. So being able to kind of map that actual in we'll call it near real time is the class of models that have fast actuals, and you need actuals to really calculate performance metrics. We'll get into some of the other classes here, or common cases that we see that don't have fast actuals. The fast actuals is kind of the happy case, but oftentimes we see significant delays. We're talking months or even years. One example of this is with credit lending or lending, where you're issuing a loan and your model's intended to predict whether they will default or pay back in full that loan, right? So it's hard to measure performance or to wait until that loan is paid back in full. And if it's a mortgage, that could be decades, right? It's hard to wait for such a long period of time in order to calculate your performance. So in this case, you may want to create kind of proxy metrics, and there are creative solutions on how to do that. In that same use case, right, for lending, one thing that we often see are biased actuals. So biased actuals are, for example, actuals that are tailored towards a specific prediction result. So in the case of lending, you are only really getting actuals whether someone paid that loan back in full or whether they were not able to and defaulted on the loan for loans you issued, right? So biased actuals in that case, you're only getting back that ground truth for loans that you issued, right? For everyone that you denied, you have no real idea or way to compute the performance of that model, because what if you denied someone that was able to pay back that loan? And in many cases, there are even models that are not able to collect ground truth in production, or just a small percentage of ground truth. So few or no ground truth, maybe an image classification model where you really only get back 1% of the click-through rate for a plethora of images that you present the user with. And so you're kind of dealing with how to measure the unmeasurable. And again, there are kind of creative solutions for approximating ground truth data, which probably deserve its own presentation. I think one thing to note here is that performance analysis from a true ML observability platform means going beyond a single performance number. In the case of credit card fraud, where less than 1% of transactions are truly fraudulent, a model that just outputs a naive, we'll call it a model that just continuously outputs not fraud, could in essence be 99% accurate. But that's masking the true color of your model, right? So being able to kind of drill down and assess cohort level performance, right? And in this particular case, one of our partners, overall model accuracy was 90%, which might even, be satisfactory to leadership, which doesn't know any better, right? But not only were you losing this kind of middle tier of people with low FICO scores, but especially low performance on people who had recently defaulted. So a solid ML observability platform will be able to look at these performance slices, so combinations of feature value pairs, and identify lower performing cohorts, surface those up in an automated fashion, and then again provide insights on how to improve, whether it's upsampling, whether it's to shift your model to a more hierarchical technique, and knowing how to kind of improve those lower performing cohorts going forward. And so again, just kind of one final visualization on how to troubleshoot. Again, a monitor should be triggered in your ML observability platform. It's able to kind of surface these feature slices that are lower performing, in this case, for FICO ranges between 300 and 499. Why are these slices underperforming? Being able to correlate that across different input values or drift perhaps, and then providing recommendations on how to fix that data. Speaking of data, bad production data is one of the most common issues we hear across industries and use cases, and the importance of data quality ingested into a model is often very correlated with the predictions that your model outputs. And so some ways that bad production data is currently handled is just dropping the predictions overall. So that could lead to kind of a filtered view or a biased state of your model's predictions. Maybe you're setting a default value, which in essence can create this drift or even introduce data leakage if done improperly. And one thing that we see often, believe it or not, is actually doing nothing, which is the simplest, but not always possible to kind of throw an error if, for example, in the visualization that you see here, we're collecting age data. However, that information is not always available to the model. So again, a strong ML observability platform, some measures that you can take here are really empowering early detection for data quality issues that you'll see across your inputs and outputs of your model. Missing data, maybe it's empty values or null values. Being able to flag out of range violations if you're expecting, if you have some P1, lower and upper bounds, being able to kind of identify when something is completely off the charts. Surfacing cardinality for categorical or discrete variables, and identifying also, hey, I was supposed to get string variables in here, and all of a sudden something changed to numeric. So being able to identify and surface these type mismatches, as well as any peaks or valleys in expected traffic. And finally, explainability. There are different ways to think about explainability. And I think it's really key to understand that in some cases, you may care about a global level feature importance. So across all my predictions, what were the most important features? And that will help you kind of set different thresholds for your monitors to, again, kind of proactively alert before core business metrics are degrading or before there's a PR disaster, right? There's also this cohort level where across predictions in certain states or across certain feature values, which features have the greatest influence. And this is also extremely important when you're assessing kind of overall model drift, right? So you can have some sort of combination that your ML observability platform is able to surface in terms of feature drift impact. So what is the level of impact or negative impact for that matter from a feature standpoint that is affecting your overall model's output, your overall model output. And then in many cases, especially in highly compliant and regulated industries where specific individual prediction explainability is necessary. Why did I not issue this person or this entity alone? So again, there's an entire aspect here around fairness, bias, and also auditing, right? Being able to explain why your model acted in the way that it did. And some other considerations as you kind of build out or adopt an ML observability solution, there's lots of fairness and bias research going on. I was part of Google's Responsible AI initiative, and I think that being able to make sure your models are not acting in a discriminant way towards specific gender, race, or intersectionality is an extremely noble measure that every company, big and small, should take. There are a number of kind of service metrics that I did not talk about today, but things like inference latency is a common metric that teams use. Outlier detection, so not just out of range values, but other univariate and multivariate outlier detection. And also this entire realm of kind of not tabular, but unstructured data. So being able to look at embeddings and embedding drift, handling images, natural language processing, and audio for all different types of models. And finally, actually, a lot of people from here reached out to me yesterday after seeing that Arize raised the largest Series A in the ML observability space. We were on TechCrunch's front page yesterday, and they mentioned to me that they were excited to tune into my talk. So I just wanted to give a quick shout out to the Arize team and to everybody working in ML observability and recognizing the strong need for deep understanding of your model throughout the model development lifecycle. And a final kind of boast is we're hiring, so please reach out to me on LinkedIn or Twitter, and I look forward to connecting with you all at a later venue.
Thank you so much for your presentation. I really enjoyed it, honestly. So I'm actually currently working on building the observability side of one of our modeling production, and it's a hard problem. Yeah. Okay, so we have a couple of questions. Please, people, post other question in the chat. We have time, so don't be shy. The first question is, in Drift, what is the good way to establish the metrics of distribution? Any generic way for various type of data like image, text, voices?
This is a phenomenal question, JT. Drift metrics are often calculated in a number of ways. There are some common statistical metrics that people use. Population stability index is one that's common in fintech and banking. There is, and population stability index is a symmetrical calculation between changes over distribution. For an asymmetrical version almost of PSI, there's something called KL divergence. A third one that's really popular is Wasserstein distance, often called Earth movers distance. So there's actually a number of different metrics. I think your specific question is mentioning image, text, and voice, which oftentimes come in sorts of embeddings. And actually, we are, this is an active area of research for Arize, which I get really excited about. So being able to use kind of t-SNE and UMAP plots to measure the thresholds of changes across your embeddings projected into kind of this 2D space. So actually, this is probably worthy, again, of its own presentation. So if you'd like, I'm going to drop my email, and we can connect on LinkedIn and kind of hash, talk about this to infinitum.
Awesome, thank you so much. Next question is, what if the way a distribution is derived significantly differ from the way your model sees the input data?
What if the way a distribution is derived significantly differs from the way your model sees the input data? So this is another really great question. So I think here what's being referenced might be feature transformations as kind of inputs into your I guess input distribution versus the way that your model sees that data later when you're collecting actuals or in a different environment. Actually, I would be really eager to kind of take this conversation offline, both around the drift metrics distribution as well as how to kind of significantly differ, how to handle when the input values significantly differ. And JT, I see you said, I have good experience in callback and KL divergence when doing research in protein structures. Awesome. Yeah, I look forward to chatting about that later.
Okay, so we do have another question. So is this used to stand as a standalone platform? How can it be integrated with other MLOps pipeline platform, for example, to do model retraining?
Yeah, phenomenal question. I think one of the core things that Arize, which I can speak to, but really any good ML observability platform should empower, is strong, flexible integrations and configurations with MLOps pipelines. at the infrastructure level, being able to kind of integrate with an infra level platform, and expose things like webhooks for model retraining. So we actually have a plethora of clients that are using different monitoring capabilities to trigger PagerDuty alerts or any other incident, to immediately fired alerts, immediately triggering Jira tickets or Slack notifications. And then people on the other side of the ML observability kind of life cycle, who use webhooks to trigger Amazon Event Bridge retraining events. So within Arize, actually, what you can do is kind of automatically surface these lower performing cohorts, and then immediately just export those slices of data in order to upsample and kind of trigger that retraining. And something I unfortunately did not get to cover today is this incredibly powerful comparison flow. So being able to compare kind of a candidate model to an existing incumbent model in production, and being able to understand whether you should promote that candidate model after you triggered an Amazon Event Bridge kind of retraining event using that upsampled data set.
Thank you so much for your answer. We have other questions coming, so nice. The next one is, when working with NLP using embeddings, how do we identify drift and biases?
Yeah, I think this is a really great question, and again, one that I can kind of talk about for hours on end. There are a number of creative solutions that we're currently working on with kind of dedicated researchers on this topic of being able to identify different ways of measuring distribution changes when projecting embeddings into kind of this 2D space. And perhaps, again, we can kind of maybe take this entire, I see I can type in here. I'm gonna actually just drop my email and encourage folks to kind of email me with this overall drift, unstructured data conversation, so we can talk about this offline, because I don't think that in the course of this short Q&A, I'll be able to address all the exciting work that we're doing in this space.
Thank you so much. Okay, so the next question is, could you please clarify the role of model explainability with respect to monitoring model drift? Please clarify if there is any correlation between model explainability and model drift.
I'm loving the questions here. These are all great. So a really great question. I think what's being referenced here is many times when a model is drifting, a model's output or predictions are drifting, oftentimes you want to understand the root cause of what affected them. And so model explainability, being able to take in things like lime values or SHAP values, any other feature importance measures, what that's able to do is provide you with kind of this very specific correlation between your prediction drift and your model's feature level impact on that prediction drift. So there's a correlation between the features, and even sometimes you can look at the kind of feature level drift and see if there's any correlation between your model prediction drift and your feature drift. But additionally, the explainability component of being able to visualize and correlate importance values, feature importance values through SHAP values, lime values, or any other feature importance metric that you want to support, can help you draw a better understanding as to what might be affecting the overall performance. I mean, this extends beyond drift, right? So overall performance of your model as well.
Awesome. Thank you so much. I think this one was our last question. So let's maybe wait 1 minute and see if people decide to ask any other question.
Awesome. Well, again, thank you so much, everyone, for joining, and I look forward to connecting offline. And a lot of these questions are, in my humble opinion, worthy of their own hour-long discussion. So I encourage you all to reach out and to kind of keep up. If you go to Arize, arize.com, I mean, we've got a blog. We publish content very, very frequently, and we're often kind of working on and exposing a lot of the state-of-the-art research that's coming out of our diverse team. So I look forward to connecting with you all.
Thank you so much. I will probably shoot you also a message because I have one of these long questions. But meanwhile, we got another question. So if you don't mind, I'm going to read it.
Sure,
Does
yes.
explainability really explain the drift, or it is just explaining why it just made the prediction and which feature influenced it to make that decision? It's a little bit complicated.
Yeah, no, that's a great question and a great clarifying point which is made here. So in many ways, explainability and feature importance does provide insights as to which top features influenced the decision, and as well as kind of what a prediction was dependent on, right? So if you made a decision to approve or deny a loan, the feature importance and those feature value combinations could provide rationale behind that decision or more transparency around the decision. But I think this is a really great distinction and question that deserves, again, just more time to discuss. I think, especially as of recent, there's been kind of this overall consensus that we shouldn't just accept ML models as black boxes. And now people, for the right reasons, are emphasizing the need to understand why models are acting in the way that they did, to be able to explain and identify what features influence the decision and which ones are most influential for that matter, and the different kind of feature values that are affecting things like drift or things like performance.
Awesome. Thank you so much. Okay, I don't see any other questions, so we're going to close here. Thank you so much from ML Ops to be here today and for your great presentation. Thank you so much.